and very good morning to all of you. I welcome you to this new video in which I'm going to discuss uh, interlinkages between production functions, marginal rate of technical substitutions, and elasticity of substitution. My dear followers, students, ladies and gentlemen, watch this video till then so that you could understand the whole concept. Let me start with the simple definition of production function. Production function is basically the physical relationship between the inputs and outputs, and it is usually formalized by a function of the following form, that Q is a function of K, L, M, and so on, where Q is the level of output, and K stands for capital, L stands for hours of labor, M stands for material, and so on. The firm's production function for a particular good Q can be expressed as a function of capital and labor, and it shows the maximum amount of the good that can be produced using alternative combinations of capital and labor. After defining production function, we may think of the marginal physical product, which is in addition to the total output that can be produced by using an additional unit of the input while holding all other inputs constant. Mathematically, we can derive marginal physical product of capital as partial derivative of Q with respect to K, and similarly, marginal physical product of labor can be found out by taking partial derivative of Q with respect to labor. We also know that there is the marginal productivity of an input is going to diminish, so we may also discuss this. And mathematically, the assumption of diminishing marginal physical productivity is an assumption about how second order partial derivatives of the production function behave in the limit. So it means that if we take the partial derivative of marginal physical productivity of capital with respect to capital, that is equal to curly square f divided by curly k square, and that is equal to fkk, where that is the second order partial derivative of k, and that is less than 0. So this means that as we increase the employment of capital more and more, then ultimately its productivity is going to diminish, and it means that the marginal productivity of an input k is going to increase at a decreasing rate, and finally that reaches maximum and then it decreases. Then we have the partial derivative of the marginal physical product of labor with respect to labor, and that is equal to f double L, that is the second order partial derivative of the production function with respect to labor, and that should be less than 0. So it means that marginal productivity of inputs like capital and labor are going to diminish as we imply more and more of that input. Changes in the marginal productivity of labor over time depend not only on how labor input is growing, but also on changes in other inputs such as capital. That is, we must also be concerned with the partial derivative of the marginal productivity of labor with respect to capital, that is the second order cross partial derivative. And in most cases, the second order cross partial derivative of labor with respect to capital is positive, which means that declining labor productivity as both I and K increase is not a foregone conclusion. In fact, it appears that the labor productivity has risen significantly since Malthus' time, primarily because increase in capital inputs along with the technological changes have offset the impact of decreasing marginal productivity alone. After discussing marginal physical productivity of the inputs, we may also discuss average physical productivity of labor and capital. The average productivity of labor is equal to total product divided by the labor inputs or the production function divided by labor. That is, we divide the total production by the input by the labor input or by the units of labor. Similarly, average productivity of capital is equal to total output divided by the units of capital used in the production. Uh, Let us also discuss isoquants and the marginal rate of technical substitutions. Isoquant, just like indifference curve, shows the various combinations of capital and labor which can produce a given level of output, say for example Q naught. And mathematically, an isoquant regards the set of K and L that satisfied that the function of K and L is equal to some given amount of output given by Q naught. In this figure, you can see that there are two inputs, labor and capital. Labor is measured along the horizontal axis per period, and the amount of capital input is measured along the vertical axis. There are three isoquants. Q shows the output level is equal to 10. This second isoquant shows that the amount of output, the given amount of output is equal to 20 units, and this higher isoquant shows the amount of output equal to 30. So the higher the isoquant, the higher the level of output. Here, if we look at this isoquant, there are two combinations. One is A and one is B. At B, LA units of labor and KA units of capital are used, and they are this combination is capable of producing 10 units of output. There is another combination B, which implies LB units of labor and KB units of capital, and this combination also is capable of producing output level equal to 10. So all combinations on this indifference curve will produce 10 units of output. Similarly, combination on this isoquant will be able to produce output level equal to 20, and so on. Uh, Now the question is, what is the marginal rate of technical substitution? Marginal rate of technical substitution is the rate at which one input can be substituted for another while holding output constant along an isoquant. Mathematically, marginal rate of technical substitution of labor for capital is equal to the negative of the change in capital divided by change in labor while output level is kept constant, that is Q is equal to Q naught. We know that the production function Q is a function of capital and labor. If you take the total differential of this function, we get that change in Q is equal to partial derivative of Q with respect to K times change in the capital plus partial derivative of Q with respect to L times dl, and total change in the output will be equal to 0. So it means that if we change the amount of capital and amount of labor along the same indifference curve, then the output will remain the same. Uh, Remember, partial of Q with respect to K is the marginal productivity of capital, and partial of Q with respect to L is the marginal productivity of labor. So if we rearrange this, we get the marginal rate of technical substitution is ultimately equal to the ratio of the marginal productivity of labor divided by marginal productivity of capital, and this is also equal to the negative of dk over dl while holding the output constant. Uh, as I mentioned, therefore, the marginal rate of technical substitution is given by the ratio of the two inputs marginal productivities, that is marginal productivity of labor and marginal productivity of capital. This equation, that is equation A, shows that those isoquants that we actually observe must be negatively slowed, because if we want to increase the amount of labor, we will have to decrease the amount of capital, otherwise the output will not remain the same. So that is why there is trade-off between the quantity of labor and capital implied. Since both marginal productivity of labor and marginal productivity of capital will be positive, that is non-negative, because no firm would choose to use a costly input that reduced output. So the marginal rate of technical substitution will also be positive, because if marginal product of labor is positive and marginal rate of capital is positive, then the ratio of the two productivity will also be positive. So that is why marginal rate of technical substitution will be positive, or perhaps zero if um, the ratio of the two productivities is equal to zero. Since the slope of the isoquant is the negative of the marginal rate of technical substitution, any firm we observe will not be operating on the positively sloped portion of an isoquant. That is why the regular isoquants are positively sloped. Although it is mathematically possible to devise production function whose isoquants have positive slopes at some points, it would not make economic sense for a firm to choose for such input choices. So, in economic sense and intuitively, in reality, isoquants, just like indifference curves, are negatively sloped. So, the relevant portion of isoquants in economics are those which are negatively sloped. Uh, the previous equation in the previous slide might lead one to conclude that an increase in labor accompanied by a decrease in capital would result in a decrease in marginal productivity of labor and an increase in the marginal productivity of capital, and therefore a decrease in the marginal rate of technical substitution. But the problem with this quick conclusion is that the marginal productivity of an input depends on the level of both inputs, not only one. So changes in labor affect marginal productivity of capital and vice versa. It is not possible to derive a diminishing marginal rate of technical substitution for the assumption of diminishing marginal productivity alone. To see why this is so mathematically, let us assume that Q is a function of K and L, and that if the marginal productivity of capital and marginal productivity of labor are positive, the marginal productivities are positive. Uh, Also assume that the second order partial derivative of capital and second order partial derivative of with respect to labor, that is the marginal productivities are both diminishing, they are less than zero. So this means that if we take the derivative of the marginal productivity of capital with respect to capital, that is negative, less than zero. Similarly, change in the marginal productivity of labor with respect to capital, that is the second order partial derivative of labor, is also negative. So it means that the marginal productivities are diminishing, they are going to decline. To show that the isoquants are convex, we would like to show that change in marginal rate of technical substitution with respect to labor is negative, that is less than zero. Because marginal rate of technical substitution is the ratio of the partial derivative of output with respect to labor divided by partial derivative of the production function with respect to capital. So, change in marginal rate of technical substitution divided by change in labor is equal to a change in the ratio of marginal productivity of labor and marginal productivity of capital with respect to labor. Since partial derivative of the labor and partial derivative of K, that is the marginal productivity of labor and marginal productivity of capital are functions of both capital and labor. We must therefore be careful in taking the derivative of the expression as mentioned above. And for your convenience, I have put it here. And this is the derivative of marginal rate of technical substitution with respect to L, which is equal to this ratio. And using the fact that change in K with respect to capital is equal to the negative of the marginal productivity of labor divided by marginal productivity of capital along in a isoquant. And according to the Young theorem, the second order cross partial derivatives are equal. So, change in marginal rate of technical substitution with respect to labor is equal to this. Since we know that marginal productivity of capital is greater than 0 and the denominator of this function is positive, hence the whole function will be negative if the numerator is negative. Because the partial derivative of the second order partial derivatives with respect to labor and capital are both assumed to be negative. The numerator definitely will be negative if the second order cross partial derivative is positive. And if we can assume this, we have shown that change in marginal rate of technical substitution with respect to labor is less than 0. That is, the isoquant are convex to the origin. After discussing marginal rate of technical substitution and marginal productivities of input, it's time to define and discuss the elasticity of substitution. For the production function Q, f of k and L, the elasticity of substitution measures the proportionate change in the capital labor ratio relative to the proportionate change in the marginal rate of technical substitution between labor and capital along the isoquant. That is, uh, this sigma is equal to percentage change in the capital labor ratio divided by percentage change in the marginal rate of technical substitution. And simplifying this, finally, we get that this is equal to change in the natural log of the ratio of capital and labor divided by change in the natural log of the marginal productivities of labor and capital. Since along n isoquant, the capital labor ratio and marginal rate of technical substitution both move in the same direction, the value of the elasticity of substitution is positive. If the value of the elasticity of substitution is high, then the marginal rate of technical substitution will not change much relative to capital labor ratio, and isoquant will be closer to linear. So it means if the value of the elasticity of substitution is high or very high and it approaches infinity, then the isoquant are more or less linear. They are like linear. On the other hand, if the value of the elasticity of substitution is low, it implies a rather sharply curved isoquant. The marginal rate of technical substitution will change by a substantial amount of the capital labor ratio changes. Generally, it may be possible that the elasticity of substitution will vary as one moves along n isoquant and as the scale of production changes. Often, however, it is convenient to assume that the elasticity of substitution is constant along an isoquant. If the production function is also homothetic, then since all the isoquants are merely radial blows up, blow-ups, the elasticity of substitution will be the same along n isoquants. Uh, Having a final discussion on this, a positive value of the elasticity of substitution implies a certain degree of substitutability between the production inputs. It means if the value of the elasticity of substitution is greater than zero, then the two inputs are somewhat substitutable. There is some degree of substitutability between the two inputs involved. For extreme case of perfect substitutes, when the two inputs are perfectly substitutable, elasticity of substitution approaches infinity. So in case the isoquants are a straight line, in that case the substitution between the two inputs is infinite. On the other hand, if the elasticity of substitution is equal to zero, it means there is no substitution possible between the two inputs. So the inputs cannot be substituted for one another. And in that case, the two inputs are perfect complements rather than substitutes. Therefore, uh, one cannot be implied without also implying the other. And we may give an example in car production. Uh, in real sense, wheels require tires, so neither of them is sufficient on its own. Thus, wheels and tires are perfect complements. One wheel will need one tire, two wheels will need two tires. So, this is the case of perfect complements, and there is no substitutability between tire and wheels. They are both perfect complements. Generally, elasticity of substitution changes at different points along an isoquant. For example, it may be harder to swap machines for people, so there is a low elasticity of substitution when only a few people are involved in the production. On the other hand, it is easier to introduce machines when there is a high degree of substitutability, while there are still enough people to run the machines. However, as a special case, there is one case in which the elasticity of substitution is at a constant level of any combination of production function. Uh, sorry, let me say it again. However, a special case is the one in which the elasticity of substitution is at a constant level for any combination of production inputs. That is, elasticity of substitution is the same value at any point along the isoquant that represent the production function. And what could be that production function? This explains why the assumption of constant elasticity of substitution CES is popular among economists while studying production. The best known example of CES production function is the Cobb-Douglas production function, where the elasticity of substitution is constant. Ladies and gentlemen, this is a very informative discussion on production function, margin productivities, margin rate of technical substitution between the inputs, diminishing margin rate of uh, technical substitution, convexity of the isoquants, and elasticity of substitution in case of inputs where they are perfect complements, where they are perfect substitutes, where there is certain degree of substitutability between the two, and where there is no substitution possible. I hope you enjoyed this. Kindly subscribe to the channel, and don't forget to click on the bell icon so that you can get regular notifications about my other videos that I'll upload for you. Thanks for watching this video. Kindly share various videos of this channel in various WhatsApp groups and on social media so that these could reach to many people and